Hi everyone, thank you for tuning in. Today what we're going to look at is another measure of complexity. We're going to look at Lempel Ziv complexity. So before we jump in, we're going to look at some background, we're going to do some reminder of some concept, and then we're going to go into the more technical stuff about the algorithm. So first, what is complexity? There's many definitions depending on the context. Here just an example, we have computational complexity, which is big O. This means that when you increase the amount of input an algorithm has, how long will it take to run? Some algorithms are really poor, they do it in n factorial time, so n here is the number of input, and some others do it in linear time, others does it in constant time, which is the fastest way, let's say. This is in a nutshell. There's other measures of complexity like network complexity. Here we're talking about graph theory stuff. Just for example, there's the B index, highly complex graph. Let's say this one. You can say this graph is complex depending on many attributes. One attribute that we say that a graph is complex is what we call a small word network. So this means that most nodes are not neighbor of each other, but you can go to one node to another in a small number of hops. So the distance is small while they're not neighbor. So what type of small word network is the brain, and it's highly complex. So this is not the topic of today. We're going to look at algorithmic complexity. One measure of complexity we already saw was the Kolmogorov complexity. The link for the video is in the description. Right now what we're going to look at is Lempel Ziv complexity, which is related to Kolmogorov complexity. So this matrix was invented by those two researchers, Dr. Lempel on the left and Dr. Ziv on the right. They teamed up in 1976, yes, to release their paper on this. Its name is On the Complexity of Finite Sequence, and then subsequently they worked again for 2 more years to build some interesting algorithm we're going to see at the end. But yeah, if you want to feel like an underachiever, just look at their Wikipedia page. It's really fascinating. So that's the context. So let's dive into the algorithm. We're going to first look at some pseudocode, and after that we're going to look at some Python implementation of the pseudocode. So the algorithm is really simple. The behavior of the algorithm in a nutshell before we look at the pseudocode is you have a piece of data, a data stream, and you read it from left to right. This is important. You read the first few bits, and if you don't see, I've never saw these bits before, you put them into an exhaustive memory. If you saw them before, you're not putting them in exhaustive memory. For instance, if you have 0, 0, 0, 0, 0, 0 all the way through, you saw it once, you put it into memory, and then all the subsequent 0 are like repeating a pattern of what you already saw. You start from the beginning, and then you try to find how a component that you already saw that explain as much as possible the next chunk of data. And then when the streak is broken, then you put that new component into your exhaustive memory, and then you repeat until there's no more bits to be read. So this, the length of your exhaustive memory, the component inside them, is the complexity index. So let's look at the pseudocode and some Python implementation. Okay, so let's look at the pseudocode for the Lempel Ziv complexity. So it's really simple, it's not that hard. So here what we have is a bunch of variables. We have the binary sequence. So here we have the 0 and 1, but we can have like any symbols that we want. This is the stream, this is just an index. Here this is the complexity, and U is the length of the current prefix, like they said. So how big is the left side of what we already saw, and V is the length of the maximum component that we saw that explain as much as possible what's happening on the right. So we basically loop until we're done with the full length of the stream. So here n is the length of S. So here what we do, if at the spot we're currently at, right, is the same as the prefix plus the length of the component, so just a bit to the right. Then we increase the length of the component, and the goal here is when we fail here, we try to find the maximum component length, right? And then if the index we're at is the length of the prefix, so let's say it was maximum of 3. If let's say we're at 7 because we find a big prefix of a big component of length 7, here we're gonna stop because v here is 7, I will be 3, and then we're gonna stop this. We're gonna increase the complexity and then move our prefix by the maximum amount we can here, and then we reset everything back to what it was, and we could keep on doing this. That's basically the behavior of this whole algorithm. So this whole thing is a bit messy. Honestly, there's a lot of variable names. It's hard to understand. So here I did a Python implementation of the complexity index, and basically we have a stream that we give of data, right? That is read from left to right. The complexity is 1 at the beginning because no matter what we have, the base complexity is 1. And then the prefix length is 1, length of the component is 1, the maximum length is also 1, and here the pointer is at 0, basically. So while our prefix a plus or length of the component is smaller than the stream, we continue, we keep on doing what we do, and then this is the same thing, right? So we're directly indexing into the stream. So if the pointer plus the length of the component minus 1, this is just for indexing, is the same as the prefix length plus the length of the component, right? So remember, the prefix length at the beginning is 1, and then it increased by the biggest component we found. So if you found a component of length 100, it will be 1, and then it will be 101, because we have basically 2 things in our exhaustive history. So this is the check to see if the way we're moving with the component is explaining whatever we're seeing on the right. So here we're just increasing the length of the component, and we keep on iterating. At some point this will be false, right? At some point the stream of numbers in the left and in the right will be different, and then here this is what happened. We check what is the maximum length of the component what you found so far. So here it basically is our length of the component bigger than the maximum length that we found. Let's say we found 3 here, and then we have like 100. This length of the component is 100 now. Then we increase the pointer by only 1, and what we do, if the pointer is equal to the prefix length, this is where we stop, right? Because this pointer tells us where we're looking on the left side of where is the component starting on the left side of the stream. It's pretty much it. And then after that, what we do, if we looked at every possible combination of starter pointer for the left side, we just increment the complexity by 1 because we found something. We have to find something. The worst case, we found only the biggest component we found was 1 bit, so it doesn't matter. We increase the complexity by 1, we move the prefix length by the maximum length of the component, and we reset some variable. That's pretty much it. So one thing to keep in mind here is we're not keeping track of the exhaustive history, because that will be that is not useful here. It takes memory for nothing, and we're just interested in looking at the complexity. If we were keeping track of the exhaustive history, this will start to become like LZ77, which is a compression algorithm. So let's look at what's happening. Here we have a big complex binary stream, so I just randomly type this stuff, and here we have a non-complex binary stream, 1 0 1 0 1 0 1 0, whatever. So here this guy will be quite big. It will be of complexity 8. Alright, so let's look at a bit more in depth about this stream of data. We have 1 0 1 0 1 0, whatever, all the way across. We get 3 over here. Let's look at what's happening. So at first we have over here we had 0 plus 0. So this is stream at 0, and here we have 1 plus 1 minus 1, so we have 1. Are the two equal? No, right? Because we looking at 1 versus 0, this is not equal, so we go directly over here. We have a component of size 1, and this gets 1 equal to 1. We increase the complexity by 1 directly, so 1 become our first component, and then prefix length become 2 actually, and the pointer go back to 0, right? And everything else go back to what it was before, which is 1. So here we have prefix length equal to 2, and here we have the pointer being 0 and the component here being 1. So we're gonna go back here. This is still at index 0. Here we have 2 plus 1 minus 1. We have basically 1. So we're comparing the first bit with the second bit. So here it's 1 versus 0. Is the two thing the same? No. So again, we go over here, right? We increase the complexity again, and we're gonna do prefix length plus 1. This is gonna be 3, right? So now we have this in our history and this also in our history, right? So we have 1 and 0. Then we're gonna look over here, right? Here we're still at 0, and here we're at 2 actually. So we're comparing 1 and 1 together. Are the two the same? Yes. So we're comparing this guy with this guy. So this is the same. So what do? We increment the length of the component. So we do plus 1. We have actually, here we're going to look at index 1, and here we're going to look at index 3, right? Are the two the same? Yes, they are. We're over here, and we're looking at over here. And if you get it, we're just going to increment the length of the component, and then those two things will keep on switching place, and the component that you're going to get is super huge. It's actually, well, the component is small, sorry, it's 1, 0, but it's super, it affects the rest of the stream. So this whole thing is not that complex because we have only 1, 0 and 1, 0, the component 1, 0 as the exhaustive history. So yeah, that's it. So now we know how this algorithm works. Why is it even relevant? We're going to see the significance of this. First of all, this was released in 1976, and in 1977-78, Lempel Ziv put out two algorithms that are really important for lossless compression, and those algorithms are still being used today with in a modified form for some of them in different algorithms for compressing the data. So those two algorithms, they are dictionary coders, so they keep track of the exhaustive history. So both are based on Lempel Ziv complexity, but they are doing it in a slightly different way. LZ77 work with the sliding window, so it has like a short-term memory of a fixed length, and LZ78 work with the dictionary and replace the actual occurrence with the reference of this big dictionary. Yeah, that's basically how both of them work. This was really important for practical purposes, but also the Lempel Ziv complexity was important for making other type of complexity in this. So one of them is the perturbation complexity index, and it's in a totally different field. It's in neuroscience research. So basically, it's a measure to find how complex the brain response is given a stimulus. So here, let's say we give a transcranial magnetic stimulation pulse, so TMS pulse to the brain. We look at how the brain responds to that, and then we can rank different people based on their complexity. So for instance, if you're sleeping, your complexity will be smaller than if you're awake. If you have if let's say you have disorder of consciousness and you're like in a vegetative state, your complexity index will be really more small than, let's say, someone that is fully conscious. So we can delineate conscious state robustly with this index. So let's just look at it quickly how it works. Right. So you give a lot of TMS pulse, you average across the trials, and then after that, what's happening is that you have a region which is more activity than others, and then you threshold this region to get a binary matrix. So here, this is the gray stuff over here, right? Here before it's weighted, and here it's binarized. So you threshold it, let's say, to the top 10% of the activations, and then what you do is for each region in the brain, you encode this through times, and here you have let's say the trace across time of this TMS pulse, what's happening. Then you compress this this stream of data basically with Lempel Ziv compression. So then you normalize it and you get a PCI index, a perturbation complexity index. So with this number we can delineate conscious state robustly. That was just an example. In conclusion, those two researchers did a great job at making an indices that is both highly practical with for the lossless compression, and also that has a higher reach to other field than computer science. So thank you for listening. The reference will be in the description if you want to know more. If you have any questions, let me know in the comments.